Alrighty, well, I will get started. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to help us use this time wisely, that we just understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. So I have an example. But before I do that, let me just read through mission 10 here and see if I have any advice for you. Don't do it. Okay, Kakashi Hitaki. Let's see here. Problem 109 is a Kepler's law problem. We more or less worked that a couple days ago. Problem 110, I don't think I have much to say about that one. 111 and 112, pretty much related to things we've already done. Problem 113, I need to do an example. I have not done that yet. So problem 113, I need to show you something today, like 113. Problem 114, a ninja concentrates his considerable power and throws his opponent vertically at a speed of 10 kilometers a second. Find the maximum height. Notice that this is under the escape velocity, so this is actually not a he doesn't come back question. This is a he comes back eventually question, but probably pretty far out, right? 10 kilometers a second. Let's see here. Problem 116, a uniform sphere of mass m is located near a thin uniform mass m, length L. So for problem 116, let me just be sure let me add another variable to it just to make it more concrete so we can all have similar looking answers. So I think that there's a thin rod like this. It doesn't really say in the problem that it's vertical, but I indicated it was vertical the other day, and the length of the uniform rod is L. All right, but the mass I was talking about is somewhere down here, let's say. I think I used a big M for the uniform sphere. Yeah. This is little m. So it would be useful to have a label for this distance right here. What do you guys want to call this? What's that? R? D? RDRR? What are we talking about? D? All right. D it is. There we go. So let's call that distance D. So your answer will, of course, depend on D, right? Okay, so enough about that. I think you want to approach that problem 116 similar to the way we worked the horizontal bar problem in here. Problem 117, I have a sphere of mass m has constant density spread from 0 to big R. Symmetry suggests a particular radius r less than r. The gravitational acceleration is due to the mass inside the given radius. Apply this principle at arbitrary radius to find the acceleration due to gravity for the uniform sphere. So, so to be clear here, we're asking for the acceleration as a function of r. That's what your goal is to find in problem 117. Problem 117. Your task is to calculate the acceleration as function of little r, right? So it's going to be different inside the sphere than outside. Something interesting happens once you're outside the sphere, then you expect it to behave like Newton's universal law of gravitation. So like, I'll tell you this much. The answer should be mass m, yeah. So of course we expect that A is equal to G big M divided by R squared for are greater than or equal to r. So here's part of the answer. The question is, what should it be inside the sphere? That you'll have to think about. I will say this, the answer should definitely have acceleration being 0 at the center of the sphere, right? So the picture here is it's like a solid sphere, right? And so, you want to try to think about, if you go to this distance r, what would the acceleration be due to gravity there? It's based on the amount of mass inside that dotted line, right? That the principle here says that the acceleration is due to the mass inside. The idea is that the mass outside, it pulls in every different, it's irrelevant. So like it cancels out the mass outside. Okay, so that's problem 117. Problem 118, I'll probably do something kind of sort of like that in a minute. Problem 119, I'll kind of do something kind of sort of like that in a minute. Wait a minute. I mean problem 120. I'll do something kind of like 120. I think I did a problem like 119 last time. All right, that's a pair of moons orbiting. Wait a minute, no. A planet has mass and the moon's orbiting a moon orbits rather. Oh, that's just kind of Kepler's law. All right. Any questions? Just thought I'd talk through the problems, make sure there's nothing crazy in here that I have missed since I wrote these problems months ago. Yep.
How can you ignore the mass outside part? Because if you had a sphere and a shell of a sphere with a mass on the outside, it would still attract the center of it. So obviously it doesn't attract them.
Does anybody have an answer? I can think of an answer, but it's very technical. I'm thinking about integrating the gravity from all of the masses everywhere, and I don't know, they have to cancel out. I mean, if it's an argument by symmetry, probably it goes something like, suppose that, the mass outside that radius did lead to a acceleration there, and then you can come to a contradiction. Now this is all assuming it's a spherically symmetric distribution, though. If it's not spherically symmetric, this line of reasoning will fail. But anyway, I don't think I'm going to answer your question at the moment, but I mean, if you don't believe, then you don't believe, but that's the assumption you're allowed to use to solve the problem, so there's that. But I think more convincing arguments for that kind of question are found in Calculus 3, truth be told. So, but here we'd have to go by some kind of symmetry argument at the moment. So, I guess you can. No, I can't think of it. I'm sorry. Any other questions or comments? Yep.
Why is distance d of 116 from the center of mass of him to the bottom of the long object?
Because we defined it to be d? Yeah. That I can answer. Because we made it so. Yeah. Okay, here, let's work a problem. I will do, suppose, so this is worse than your homework, but I think it's instructive. All right, so suppose you've got a a mass, big M, all right, planet, all right, and then suppose it has not 1, not 2, not 3, 4 moons. And let's put them in the only reasonable way that they could be situated. Obviously, this picture, not necessarily to scale, but, and they're orbiting, all right? So symmetrically situated. I know we found, I'm pretty sure we found, I know we found binary stars, right? Pairs of objects orbiting each other. I'm not sure that we've ever found this anywhere else, like 4 moons just like this. But this is a solution, a potential solution to Newton's universal law of gravitation. You could have this situation, all right? And if you did, and let's assume that the moons have mass little m, all right? Then the question is, how is the radius of the orbit related to the period of the orbit, all right? Let's see if we can find the analog of Kepler's third law for this problem, all right? So how would you do it? So here's the orbital path, right? Why do the moons orbit? What's causing them to orbit? Gravity. Gravity of what? The planet, but what else? Each other. Yeah. Really? Tennessee. All right. So, pick a planet, any planet. Pick a moon, and let's look at Newton's law on that moon. All right. It's going in a circle. So let's pick the top one, because it doesn't matter if we pick any which one we want. We'll be able to figure out the question. All right. So let's pick the top one, and there we have mv squared over r. Right. That is the net force on that, because it's going in a circle, right? So we prove this. And I'm assuming that it's constant speed, right? Because this is an orbit, it's kind of some stable orbit, all right? So constant speed. And, all right, so that should be equal to the net force. What is the net force here? Well, I've got the easy thing, this one, right? So here's the gravitational force from M. What else is there? I've got also this guy, right? And I've got this guy. It's supposed to be this. It's symmetric, right? So I need to number these moons. Let's call this 1. Let's call this 2. Let's call this 3 for the sake of this discussion. So I've got F1, F2, and then of course I've also got down here, my bad, that was 3. I can't stick my own number in. So what's the situation here? If you draw a triangle here, right? You can draw this triangle, can't you? See this? This is a right triangle. What kind of triangle is this, though? See, this is equal legs, right? 45 degree. 45 degrees. So my point to you is this is 45 degrees, and this is 45 degrees. And the horizontal part of the gravitational force in my picture, that's going to cancel, right? The left and the right components are going to cancel. We just need to worry about the center seeking part. So how do I figure that? So I've got, F1 cosine 45 plus f3 cosine 45, and plus f2, and then of course plus the gravitational force from m. All right, so let's put in some details here. So we've got little m v squared over r. Now what is f1? Oof. What else? I need to figure out this distance. What is this distance here? So I probably should label the orbital distance r, all right? I mean, I've already done that there because I wrote mv squared over r. I've labeled it there, right? So if that's r, what's the distance between the moons? Ah, very good. So I heard square root of 2r. So this right here, square root of 2 times r. All right, so what's the, and by the way, so we've got what? By symmetry, we can just double this, right? So we've got 2, f1 is, what is it? G, mass of the moon, mass of the planet, my bad, not mass of the planet. This has nothing to do with the central planet here. This is just GMM divided by what? The distance squared, which is r times the square root of 2. I'm going to write it that way because it's easier. So this is Newton's universal law of gravitation. I had to multiply by 2, right? And then I have to multiply by cosine 45, which is 1 over root 2. So that right there, guys, is these first two terms. Okay? Now what's the distance from planet 2 to our top, I mean from moon 2 to our top moon? 2r, right? So that one gives us plus g m little m divided by 2r quantity squared, right? That's the gravitational attraction due to this guy. All right? Then what? Well, then I have to take care of the gravitational attraction of the planet, right? The central planet here, which is going to be big G, little m, big M, divided by r squared. So what do we got? We got a big G everywhere. We've got an r squared everywhere. So, and we've got an m everywhere, right? So my advice would be to, divide by m over r, and that gives us v squared. I'm going to factor out that g, all right? And let's see here. The first term gives me what? Oh, I guess I can factor out g over r, right? Let me factor out g over r. All right, so what I've got then, I've got this root 2 squared cancels that 2, and I just am left with m over root 2, I believe. I pulled the r out. It was, but I divided this by m over r. Yeah. And let's see here. Then what? Plus m over 4. Thank you. And that one is plus big M, just plus big M, right? Yeah. Now what is V? Remember V is 2 pi r over t. You square that. That gives me the, so this right here, we can solve, and that will tell us the relation. Basically here we have r cubed over t squared equals g divided by 4 pi squared times apparently, m times 1 over root 2 plus 1/4 plus big M. And that would be the analog of Kepler's law, Kepler's third law here. Again, the orbital radius cubed is proportional. Or the ratio of the orbital radius cubed to the period squared is equal to a constant, and that constant is characteristic of the masses which are orbiting. We found a similar relation for the planets orbiting the sun, right? Anyway, my point to you is if you can set this up, then you can solve a host of questions that are related to this, right? Like I think your homework question, what was the difference with the homework question? I think I just had 3 moons but no central planet, right? So in some sense that's easier, and in another sense that's harder, right? Because for 3 moons, how do you have to figure it out? So your homework problem, you got 3 moons, right? They should be symmetrically situated, right? That was a bad, it's sad. But imagine that this is the center point, right? So if you look at these 3 like that, what's this? 120 degrees, 120 degrees, 120 degrees, right? So that's the geometry at play in your homework problem. But the same principle applies to figure out the relation of the velocity to the orbit. You want to like write Newton's law on one of the moons in terms of the other 2 which are pulling on it. And you'll want to just select the part of the gravitational force which is center seeking because the other parts cancel out. So it's the same principle, it's just slightly different geometry. Yep.
So, that three's going in a different direction. How would you subtract that force from that force?
Oh, I'm just the sine 45. You're right. This one has F1 sine 45 minus F1 sine 45. This one has F3 plus F3 sine 45. In terms of these directions, those cancel. They cancel out. So that's why we didn't pay any attention to them. They have to, because the net force has to be center seeking for it to be going in a circle. If they didn't cancel out, then it would be speeding up in a tangential sense. But this is a good question. Yeah. Other questions? All right. So, you know, sometimes when I get to the test, I put the 2 moon problem. Other times I put a planet in a moon. Other times I put a planet in 2 moons. It just kind of depends on, you know, I don't know. It just depends. Let's see here. Oh, next example. What happened? So there's something called the Poincare Plane, which I should talk to you guys a little bit about. And so here's the idea of it. If we have the problem, something like m d squared x dt squared, right? So this is ma, all right? And that's equal to, let's say, a force, which is conservative, right? Then, of course, that's equal to minus du dx, right? And so we can do what? We can rewrite this as m dv dt, right? Plus, well, du dx. But I can take that du dx and trade it for a dx, dx dt. Well, let's see here. Sorry, let me just do a step here. It's du dx equals to 0. So here U is potential energy, right? Now if I multiply this by V, something interesting happens. So this is m v dv dt plus v, but I'm going to write v as, well, fine, v du dx. I'll do another line here. So that is ddt of 1/2 mv squared for the first term. And here, if you look at that, v du dx is dx dt du dx. So by the chain rule, you can write that as du dt. So this is actually plus du dt. I'm not telling you anything terribly new. You already knew this. If the net force is conservative, what's conserved? What is conserved? Well, the energy, right? So this is total mechanical energy. We're talking one dimension, right? There's no rotational motion going on here. It's just one-dimensional system. So what this means is you can look at the energy as a function of x and v is equal to constant for equations of motion. In other words, for physical trajectory, the energy is conserved. All right, fine. So let's see here. Let me say a little bit more. So we have v is equal to dx dt, right? This is the definition of velocity, but we also have that, let's see here, dv dt is what? F over m, right? So if you put those together, you can view them as a package deal here. Let's see here. So we have, excuse me, dx dt equals to v, all right? And dv dt is equal to f over m, right? Which is, by the way, the same as 1 over m minus 1 over m times du dx, right? So here's the neat thing. If we have a graph of potential energy, so we have a graph of potential energy like this, then we can draw right under it what's called the phase plane or the Poincare plane, where we plot x this way and velocity this way. All right? So to each energy diagram in the potential energy plane, there corresponds there's a corresponding physical trajectory in the phase plane, and you can analyze the motion using this idea. Let me give you a very simple example to get started on this. So the most simple potential energy, perhaps, that's non-trivial is the harmonic oscillator. So this is it. U equals to 1/2, kx squared. Something like that. All right? So that's a potential energy function, right? So for this, you can look at different energies. All right? So like here's one. Energy 1, all right? So that's as far as it goes in the potential energy. We've done these before, right? Draw in the potential energy diagram the possible physically reasonable motion, right? I'm adding a new part to this story, which is you can draw a corresponding curve down in the velocity position plane. So what goes on here, check this out, is drop these down like that. All right? Think about this. Where the potential energy is equal to the total energy, what's the situation? If the potential energy is equal to the total energy, the kinetic energy is 0, which means the velocity is 0. So that means I get this point and that point. All right? Furthermore, think about this. Critical point. For your potential energy means what? du dx equals to 0, right? Where your potential energy has a horizontal tangent, that's a critical point. What's the situation here? Well, dx dt is v, right? dv dt is du dx. So what's this say? This says that dv dt is going to be 0 precisely where we have critical numbers for the potential energy. And what did you guys learn about parametric equations in calculus 2? You've learned that if the second variable's parametric derivative is 0, you have what kind of tangent? Horizontal tangent, vertical tangent. Which was it? If I go back to y, x of t, y of t, you guys can tell me probably, right? dx dt equal to 0 versus dy dt. Which one of these, given that the other one's non-zero, describes a horizontal? Which one describes a vertical tangent for your parametric curve? dy dt equal to 0? Yeah, horizontal. Horizontal tangent. So this means that wherever you have a critical point for your potential energy, the curve in the xv plane, in the so-called phase plane or Poincare plane, will have a horizontal tangent there. All right? So that's something to look for. Where do you have a 0 here, right? So critical point there. So that goes something like this. These pictures are heuristic, all right? So I didn't even tell you what the mass was. It doesn't really matter. So the picture here looks something like this. And you can put little arrows in. How do you do that? Well, check it out. If dx dt is equal to v, that means that the curve is going which way when v is positive? If dx dt is positive, the curve is going to the right. So it goes like this up here, and it goes like that down there. All right? And then you can do another energy level, like this, right? That drops down here like so. And that will give you another one of these guys. And you can think about the story of the spring oscillating on this Poincare, on this plot, right? Think about it. What's going on? It's describing the spring, right? It's maximally compressed. Let's see here. It's maximally compressed here, right? Its velocity is 0. What happens? It stretches back out, right? I mean, no, it's stretched out. I'm an idiot. So maximally stretched out, duh, right? So it's stretched out the most here when x is biggest, and the velocity is what? 0. So what happens? It pulls it back in, right? As it pulls it back in, what happens? The velocity speeds up, right? It goes through its equilibrium position at maximum velocity, and then it compresses, right? At which point it hits the other side of the circle, and it's compressed, and then it stretches back. Anyway, if you look at a spring and you think about it, you can see all 4 parts of the story of the spring as it compresses and elongates and goes back and forth. You can see all of that in this XV plot. All right. So this is a complete story of the motion in the position velocity plane, and we don't even have a solution to the problem. It's all just with graphing. You see this? Like, so I can give you a more interesting function, right? Like, I don't know, this one. There you go. Here's a potential energy diagram. All right. And let's sketch the phase plane. So, rules of thumb, you need horizontal tangents wherever you have critical points. So I'm just going to, these are my critical points, right? So these are the critical points. And so let's just start out something. I'll do an interesting one, this one right here. So let's say that's energy E1. So dropping it down here, I get this point, I get that point, I get this point, I get that point. These are the places where the velocity is 0, right? Because that's where the potential is equal to the total energy. And so this one here gives you a little circle like that. And likewise over here, you get a little circle like that. Well, not a circle, an ellipse generally. Now over here, I get one of these dudes, all right? And again, it's always right moving above, left moving below. All right, let's look at another energy. What if we're, let me use a different color, right here. So I drew it so it's not quite at the zenith right there, so that it's going to be separated on one side or the other like that. All right. So there's another little circle here like that. All right. This one's more interesting because this has got what's called an unstable equilibrium. Like that. So again, what's interesting about this particular critical point where those solutions are crossing is you don't know what, if you have just a little nudge, you don't know whether it's going to stay close to that point or if it's going to go off to infinity, right? So this is an unstable equilibrium, of course, corresponding to the fact that it's like the top of a hill, right? And in fact, if we get just a little bit higher energy up here, right? Then what happens? Well, the deal is you have to go horizontal across these guys, all right? And this is just totally heuristic, but something like, let's see here, if I'm doing it right. I'm horrible at these, something like this. So they should drop back down. You can kind of imagine it. And then it kind of loops around and replicates that picture down here. Something like that. So this is the concept you use to answer that homework problem. I haven't gone through it yet, but this is how it's done. These are called Poincare Plane. Is it phase plane or phase plane? I can't spell plane. Plane, also known as Poincare plots, in honor of the fellow who thought of these. And obviously, this is a useful technique if you want to analyze the motion, but you don't actually want to solve Newton's law, right? If I have the potential energy, I can see what the possible motions are by drawing these pictures and seeing what happens, right? So these, just to, these points right here, these are called stable equilibria, right? Whereas this one, there's that in the middle point, right? If I did the energy just a little bit above the blue one, just a little bit above blue, you'd be able to see that I got an unstable equilibrium right here. So the top of potential's unstable, the potential wells are stable, as you can manifestly see from the velocity position plot down here. All right, well, I think I've said enough about those to you. Do you guys have any questions? Yes, no, maybe so? See how much time I got. All right, well, let me open up something here if I can find it. There were a couple of examples in, where were they? I want to say it was lecture 29 that I didn't go over, that it wouldn't hurt us to go over them. Hopefully I've got the right one. We'll find out soon. Oof, that does not look like the right one. Maybe I'm thinking of 30. Wow, he's loud today, isn't he? Well, that's not it either. I have there's one of these. I have an example of a pulley and a table, and the pulley has mass. You know, I was trying to find that one. Do you guys know where that is? I had it open before, and I have foolishly closed my picture. Well, if there aren't any more questions, I guess this is as good a place as any to stop for today. So, I think I went over some other day. I owe you these minutes, don't I? No. Anyway, next week we'll do fun stuff. So, see you there.